Hello. So after the derivation, we have built a circuit on TINA simulation software, and we will be simulating it. So here is the circuit, the non-inverting differentiator circuit. Here we are given the input of around 15 millivolts peak-to-peak sine wave, and we have obtained the phase and the frequency response, as you can see. Initially, we gave 1 kHz sine wave. As we increase the frequency, the gain increases. The gain reaches its maximum at around 15.8 kHz, the frequency of the sine wave, and the maximum gain is around 60 decibels. As frequency increases more, the gain gradually decreases. So this is the frequency plot of the non-inverting differentiator. We also have got the phase response here. Initially, from 1 kHz of frequency, the phase remains same. The phase between the input and the output, the phase difference, it remains the same at around 90 degrees. And reaching around 11K, the phase it suddenly drops down to around minus 90 degrees, and then as we increase the frequency, the phase it decreases more, or it increases in the negative domain. So this was the frequency and the phase response as we obtained on TINA software. Okay, so now we will implement the given circuit on the hardware provided by TI. So we are using here the ASL KB 2010 starter kit. So as you can see, here is the kit. We have already rigged it up, the circuit, and we have given plus 10 and minus 10 power supply. So initially, we are giving a sine wave of 15 volts peak to peak input. So initially we have given 1 kHz of frequency. We will be varying it and we will study the output. So initially, this is the input sine wave. So here the output is shown. It's very small at this frequency. That's why it's we are able to see it. Probably alright here. So it's quite small at this low frequency. Now, as we increase the frequency, the output it gradually increases, and as we go, alright, this is 2 kHz frequency. As we increase the frequency, the output it increases, as you can see. It slowly increases to its peak. It increases, and the frequency reaches its maximum at around 12K, and then it gradually decreases as we increase the frequency further. So you just have a look. As we increase the frequency, the output is increasing, and then it gradually slows down. So this is the non-inverting differentiator circuit, and this time we are giving a square wave input of 100 Hz frequency and 1 volt peak to peak voltage. So giving the input, we have obtained the output as this. As you can see, this green line, this shows the input square wave, and this red ringing output is what we get on the CRO. As you can see, initially the output it goes to saturation, and then slowly it starts ringing, and it gets damped oscillations. We can call it a damped oscillation, as you can see. And then it goes to 0. And then as the negative pulse of the square wave starts, it again goes to negative saturation voltage, and then it again damps, and then it becomes 0. So this ringing output can be explained as this. Here we have the transfer function as SCR1 square by R1 plus R2 divided by 1 plus 1 by A into 1 plus R1 by R2 plus SCR1. Here A is the open loop gain or the differential gain of the op amp, which is also equal to the GB by S, where GB is the gain bandwidth product. Now when we substitute this GB by S in the above transfer function, we get the equation as this: SC R1 square by R1 plus R2 divided by 1 plus into 1 plus R1 by R2 into S by GB plus CR1 S square by GB. Now if you can note, the denominator resembles the denominator of second order transfer function which comes from the control systems, and it is given by this. The second order transfer function from the control systems is given by this, and you can see the denominator is comparable to the denominator what we have got. Now comparing these two denominators, we have found that 2 zeta omega n S is equal to S into 1 plus R1 by R2 divided by CR1, and omega n square is GB by CR1, where omega n is the natural frequency of the system. So squaring this equation, the equation 1, we get 4 zeta square omega n square as 1 by CR1 the square into 1 plus R1 by R2 whole square. Simplifying and putting omega n square as GB by CR1 in equation 1, we get that zeta square is equal to 1 plus R1 by R2 whole square divided by 4 times GB CR1. For zeta we take square root on both the sides, and we get 1 plus R1 by R2 divided by 2 root of GB CR1. Now the gain bandwidth product for the op-amp is quite high. Also we have the resistance R1 and capacitor which is around 10 raised to minus 6 in microfarad range. Resistor is around 10 cube, and GB, the gain bandwidth product, it comes around in megahertz range. So overall the whole value of zeta, it goes less than 1 because the denominator is quite high. So the zeta value, it goes less than 1, which is the condition for the underdamped oscillations, and this is the reason why we are getting the ringing output here. So we are going to do this on the hardware, and we will obtain the same ringing output on the CR. So here we have again arranged and picked up the circuit as shown, and coming here, this is the input square wave, 1 volt peak to peak in 100 Hz, as you can see, 100 Hz. Now we are shifting to channel 2 here. So this is the ringing output which we have talked and which we have got on the simulation screen also. So this is the ringing output, as you can see. And the reason for the ringing is already explained.